Welcome to the Fall Corridor Theory Seminar. This is a seminar that happens every Monday at either 11 or noon. And we have a tradition of starting off the seminar with someone from our own university. So today we have our very own Jonathan from Med.
The sponsor.
Oh, right. And we have we have wonderful lunches that are being sponsored by Yahoo. And also this is also being sponsored somehow by Yahoo that we're recording it. Yeah, so thanks.
Okay, thank you, Nicole. Okay, so welcome. So this is similar to a talk I gave a couple months ago at the Game Theory Conference in Stony Brook. So it's not a paper that directly uses formal computational models anyway, but it's something very much motivated by concerns of limited computation. And I've worked that a little more into the talk for today. And I think it's very possible that it could motivate future papers which deal with computational concerns in a more formal way. Okay, so very broadly, it's about the problem of prediction. Okay, this is a very basic problem. We see a stream of data. In this paper, for simplicity, the stream of data will be a sequence of observations from a finite set. Let's say it's binary, just to keep it very simple. Okay, so we see a stream of zeros and ones. I sometimes like to talk about them as heads and tails. And at any given time, we may be asked to make a prediction about the likelihood of future events. Now, when I mean future events, I mean any set of terminal sequences, not just like one period ahead or n periods ahead. Okay, so the classic framework in decision theory for prediction is that we have a prior over the set of all sequences, right? And that would be sufficient to tell us, assuming that it's full support, that would be sufficient to tell us if we just use Bayes' rule after we see any sequence, what's the probability of any future event. Okay, and in conventional decision theory, that choice of prior is completely subjective. It can be whatever we want. So there's nothing more to say. But I think there's more to say. Okay, so let me get into that. So let's say we're observing coin flips. And so one prior distribution, which is very simple and we would commonly look at least in probability textbooks, is that we think we're looking at coin flips that are IID 50-50. Okay. Then we see a long string of H's. Okay, however many there are there. We're probably going to say our model was wrong. Okay, and that we think, oh, maybe the coin isn't really 50-50. I now think the next one's more likely to be heads than tails. And that's very different from what we would do if we were just using that IID 50-50 as our distribution and doing basic Bayesian updating. In that case, we would just ignore all the heads forever and just keep saying, oh, next one 50-50. No, I don't care if they're heads. They're all independent, and so on. Okay, so the natural way to interpret this, if you want to save Bayesianism, okay, is to say, well, the problem is not with Bayes' rule. The problem is when you said your prior was that they're IID 50-50, you didn't really mean it. Okay, you just thought they're probably IID 50-50, but not for sure. So what you said in your belief, well, that wasn't really your belief. You should have restated it. Okay, so we restate it. We say, okay, I think the coin is IID, but I don't really know for sure that it's 50-50. It might be unbalanced. 60-40, it might be double-headed, it might be being flipped by a professional magician, and so on. So, all right, I think that it's, IID, but the frequency is unknown. Maybe it's uniformly distributed in 0-1 from my point of view. Okay, and so this belief here in the first bullet point, that's going to look pretty reasonable. If you see a long stream of heads, you'll gradually converge to the belief that, yes, it's going to be all heads. That seems like a reasonable thing to do. But there are other sequences where you might find yourself, if you just strictly use this belief and follow Bayes' rule, with beliefs that you don't really believe in. So if you see alternating heads, tails for a long time, okay, if your distribution really placed full weight on it being independent just with unknown frequency, then when you see heads, tails for a long time, what happens? You just believe they're independent 50-50. Okay, you don't think that the alternation actually means anything in that case. So, after 100 periods of seeing heads, tails, you're still going to think the next one's 50-50 to be heads or tails. And that doesn't seem like it's what most of us would believe. Now, of course, so, if you were trying to be Bayesian, you started out with this belief, and then you saw this long alternation, you'd be awfully tempted to not be Bayesian anymore and say, oh, I think maybe it's actually alternating. Okay? So, but there are two ways to save yourself. One way is to, after you after you see this long alternation, you say, oh, I'm not really Bayesian. Now I think it might be alternating. The other way is to state your Bayesian belief differently at the start of time, right? So another way of saying this is, that belief that you said you had at time zero, you didn't really believe that because you thought that maybe there was a small chance it was alternating, and when you saw a lot of evidence, you decided it was. So you could say at time zero, my belief is, well, with probability 0.99, it's what's called, so exchangeable is just a fancy word for a mixture of IID. So with probability 0.99, they are, independent, possibly with some frequency different from 0.5. Okay, that's what I think is probably true, but I also think there's, a small chance that it's some other kind of process. And, I don't want to be naive, so I'm going to say that process could be a lot of things. It could be periodic, like the one I just showed. It could be some general hidden Markov process where the frequency depends on the past, and observations, okay? So maybe this is more like what I actually believe when I start seeing these coin flips. Now, the only problem with this is that I make an observation, and based on that observation, I want to make a forecast. And working with this belief, okay, which could plausibly put non-zero weight on a lot of different kinds of distributions, okay, updating that is going to be, well, I say here, annoying, okay, or, computationally, it's going to be complicated to describe to people. It might take a lot of computation power, okay? Even specifying the beliefs will be a very annoying process. I have to say exactly how much weight I put on, hidden Markov with n, dimensions of hidden parameters, something like that. Okay. So specifying the beliefs is going to be annoying. Updating them is going to be annoying. It seems like it might be a lot better to do something a little bit more like the naive person who waits until he sees a pattern, then shifts their beliefs. Okay, who says, okay, my provisional initial belief is that it's independent, maybe not independent 0.5, but independent with some frequency that I will learn. But if I see a pattern in the future, maybe I'll change my mind. Okay. The only problem with this is that there are decision theoretic objections to this, namely that it makes you dynamically inconsistent. So I'll say more what I mean by that later, but basically, there are bets you would make at time zero that will be inconsistent with bets you would make at a later date. And that's, in a way, that different from just the fact that you received information, but actually inconsistent in a way I'll make precise. So the purpose of this paper, okay, so by the way, this is like the usual argument for saying that Bayesian inference is the way to go. It would be to say that any system of inference other than Bayesian inference will make you inconsistent, and there's a certain sense in which inconsistency can be painful. You might make a set of bets that guarantee you a loss. I'll come to that later. So that's the usual reason to be Bayesian. I want to say, if you're a little bit non-Bayesian, that's okay. That's like the message of this paper. And in order to address that, then I want to say, how inconsistent are you if you do something like, start with a provisional belief, wait till you potentially see a pattern, then maybe shift your beliefs. And the main result, okay, summarized as best I can before I talk about the formalism, is to say if at the start of time the subjective probability, so the probability according to you that you reach a what I'm calling a paradigm shift, where you don't want a Bayesian update, but instead you switch to a totally different model. So if according to you, the likelihood that you reach a paradigm shift is small, then you're not very inconsistent. Okay? The main result is going to be pretty much that. Okay? All right?
There are computational approaches to this problem, too, using Kolmogorov complexity, universal distributions.
True.
That,
So you could
turn you back into being a Bayesian.
So you're saying something like put weight on the models based on their like 2 to the minus Kolmogorov complexity or something like that.
Right.
Okay, but that's like a beast to update, right?
Computationally hard, yeah.
Yeah.
But you can limit your models, your programs, and it's not as bad.
Okay. Well, okay. That's the kind of thing that I have in mind. But I'm gonna. Well, hopefully I'll say something interesting about that in a decision theoretic way. So, okay. So, so this is a, slide that I added for this audience. So, if we're concerned about actually being able to compute these predictions, then one question we're probably going to have to worry about is how we represent our belief. So, as far as decision theorists are concerned, your belief is just an arbitrary distribution over omega. Okay, but omega plausibly has a huge number of states. Okay, so it doesn't quite make sense to say that we can have an arbitrary distribution. I mean, arbitrary distribution is like a vector with 2 to the 100 elements saying what the probability is of each sequence, and we probably can't even represent that. So we're probably going to actually be representing our belief via some kind of computable function. It might be, say, a computable function that takes a history and tells you the probability that the next observation is a 0 or a 1. And, if we're asked that, so even if this function, say, was computable in reasonable time, being asked at time 0 about an event which depends on things happening 100 periods in the future, tracing out the tree through all 2 to the 100 branches, this can be, of course, exponentially bad. So, in other words, there are real limitations here, both on forming our belief in a way that we can even express, and on being able to compute things about that belief. Okay, and one obvious way to get around that would be to have a much simpler belief corresponding to a very simple computer, like the simplest thing would just be the uniform distribution, the one that I started with. So maybe you take the uniform distribution as your provisional distribution, but then you have certain sequences that are going to flag you to do something more complicated. Okay, and then your forecasting procedure is then certainly not exactly Bayesian, and it's going to have some inconsistencies. Okay, but I'm going to say something about how big those are. Or maybe we can say that those are small enough that we don't care so much. Okay. Okay. So we want to be rational. Okay. I'm assuming we're taking the point of view of a fairly sophisticated predictor, decision maker, who wants to be rational in the sense that if there's something about his decisions that's either internally consistent or that seems to be, insensitive to the data in a way that most people would say looks silly. Okay, like, still thinking it's 50-50 after you see 100 heads looks kind of silly. So he would like to both, be sensitive to the data in a way that makes him look reasonable, and he'd also like to avoid certain internal inconsistencies that you can avoid by being Bayesian. And it can be a little hard to combine those things, right? In order to both be sensitive to sequences that, people might agree ex post, oh, this sequence has a certain pattern that you should notice. And to be a Bayesian, I mean, this is hard. You would have to put those sequences in your prior at the start of time, as I've already been saying. So that's why I say being a completely orthodox Bayesian is a pain. So I want to relax that and let you be not perfectly Bayesian all the time. And this is a reiteration of the main result. If you're only non-Bayesian, rarely the inconsistency is minor. Okay, so now I'm going to start talking about some of the formalism that I need to state the result. Okay. I already told you he's observed making observations from a finite set n, so the state space is sequences of length n. It's also useful to talk about partial histories. A partial history is a sequence of any length k. The empty set symbol is useful for the empty history. Being a subhistory just means that this is an initial subsequence of this. Okay. Okay, set of all histories, H. Set of all distributions over the entire state space, okay, delta of omega. And the thing here that's not standard, okay, that's introduced in this paper is this bottom line here. Okay, so this is what I'm introducing. So I'm going to call a system of provisional beliefs any function that takes a history and returns a probability over terminal states. Okay, and you have to be consistent with the history you've already seen. Okay, so you're going to put full weight on the terminal states that are extensions of the history you've already seen. That's all that this says. Okay, and I'm letting that be any function. Okay, but all of my theorems are going to deal with the case that this is a function which most of the time does Bayesian updating, in some sense of most. Okay, and occasionally does non-Bayesian updating. Okay, but formally, it's just any function that, depending on what you've seen, what history you're at, gives you distribution on terminal states consistent with what you've seen. Okay. So let's fix, for most of this paper, we're going to assume there's a fixed f in the background. So a history h then is normal if your belief at history h, that's f of h, is formed by taking your belief at history h to the minus 1, that's, one period before h. Okay, so just taking off the final element of the sequence. So look at your belief at history h minus 1, one period before, and do a Bayesian update. If that's what you're doing, the history is normal. Otherwise, I call it a paradigm shift. Okay, and it'll be convenient to let S be the set of all paradigm shifts. That's a set of histories. Okay. And he's Bayesian if he does Bayesian updating everywhere. If the set of shifts is 0, is empty set. Okay. So a bet, okay, is a pair. So when I talk about a bet, I mean something that's offered at a certain history and offers certain payoffs as a function of the terminal state. So this V is a vector which tells you your payoff at every terminal state. H is the history at which it's offered to you. Okay. And it's going to be convenient for me to only look at bets that have 0 payoff at states that couldn't possibly happen at the history that they're offered. Okay? So you would ignore those histories anyway. You assign 0 probability to them anyway. But it's convenient for me to just say, when we're offering you this bet, we don't even bother specifying a payoff at the histories that can't happen. We just specify a payoff of 0. Okay? Now, I'm assuming basically the simplest possible form for decisions at a specific history. Okay? So this paper is about how decisions and beliefs evolve throughout time. So much as there's a huge, decision theory literature on how you make decisions at any one time, I'm going to take the very simplest version of that, where you just look at a bet, and if the expected value is greater than or equal to 0, you take the bet. And that expected value is according to the beliefs you hold at time h. So at time h, you hold beliefs f of h, someone offers you a bet v. you calculate the expected value of the vector v according to the belief f of h, and if it's positive, you like it. Okay. So you're risk neutral and using these probabilities to make your decision. Okay. Okay. So finite set D of bets is a Dutch book. So this is an important concept. This is how I characterize inconsistency. Okay, it's going to be also equivalent to a different version of inconsistency. I'll talk about that. So let's see. So this is a list of bets. Okay, these are bets. When I say, HV, I mean you're only offered this bet if you get to that history. Okay, and accepted means accepted if you get to that history. Maybe I'll finish and then. Okay. And I'm going to say that it's a Dutch book if the sum of those vectors is less than 0. So the single less than means negative somewhere and at most 0 everywhere. And it would be a strong Dutch book if it's strictly negative everywhere. Jason? No?
I have a couple questions. Remind me what little f was?
Little f is your belief as a function of the history. Yes?
But it's just a number in this context. You just multiplied it by b.
Oh, no. Those are both vectors on
That's a
dot
dot
product. Yeah. Sorry, I could have said, maybe it would have been easier to read if I said expected value sub f of h of v. Right? I mean, it's a probability distribution, but I can just look at it as a vector and dot it to this vector. Because if it's, it's a finite, it's a probability distribution over finite set. So just write it as a vector, dot it to that vector. That's the expected value.
I see.
Okay?
So v is like a component-wise bet on
Yes.
this.
V is an element of R to the omega, so it tells you what your payoff is at each terminal state.
What's the
R to the omega.
Yes.
So for every
So omega is the set of terminal
Oh,
states.
good. So f is a distribution on all omega.
Exactly. And
Good. And so that's okay.
so these are both vectors
Good.
in R to
That
the
makes a lot more
omega,
sense.
and I'm dotting them.
Okay.
Yeah.
Okay.
Okay.
So now that I understand the second bullet, the third bullet.
So wait, how big is omega? It's finite?
Yeah, it's finite. It's 2 to the
Number of rounds.
2 to the n. Yeah.
And so,
Okay.
So what's the meaning of sum of vi is less than 0? Like, I mean, I
So-
understand the mathematical meaning, but why is this?
Why is it important? So this would mean, so let's look at the strong Dutch
Actually, what is
book.
that? Is that sum over I, or is that sum over the components of v?
This is the sum over I. So this is a sum of vectors. This is a vector, and when I say it's
So it's another vector.
yeah. So when I say it's less than 0, I mean component-wise it's strictly negative.
Every component. Is like
Every component is strictly negative. So yeah. So the interpretation of this is no matter what history occurs, you have a strictly negative payoff. Okay. And depending on what history transpires, some of these bets will happen and will actually happen. Some of them will never be offered. It will not happen. But the fact that the sum of these vectors is everywhere strictly negative means no matter what happens, you wind up negative.
So the Dutch books exist.
Dutch books sometimes exist and sometimes don't. That's the topic of the next slide. Okay.
So, I mean, it should seem weird, right? Because you're saying all of these bets are accepted.
And
Right.
yet
You'd assume the person would want positive payoff.
Yes,
And yet,
you would. So the Dutch book is bad. So the existence of
And
a
yet
Dutch book, I'm
somehow-
going to treat as a form of internal inconsistency. It means you're doing something that you definitely shouldn't be doing.
got it.
Okay. Okay. So this result is, not too novel. There are, classic results that are very close to this, and just because my formalism is a little different, I reproved it. But anyway, basically, being Bayesian is what you need to be dynamically consistent, and it's also exactly what you need to such that there are no Dutch books against you. Okay, there isn't any demon out there who can look at your decision process and say, these are the bets I'm going to offer conditional on what happens, and no matter what happens, you wind up negative and the demon winds up positive. Okay? So for convenience, I'm going to say that your belief has full support. Okay? So you think any sequence at all is, at least fairly possible. It's a pretty mild assumption. So in that case, the following 5 statements are equivalent. Okay? So basically, the existence of a Dutch book, whether strong or weak, is equivalent to being not Bayesian. So you have to be Bayesian for there to be no Dutch books against you. Okay? And being not Bayesian is also equivalent to the existence of any bets at all where you're inconsistent. Okay, so let's look at this last one, number 5. So there exists legal bets empty set V and H1V on which I make different decisions. Okay, that might not sound so bad. So it means you're being offered some set of terminal payoffs at time 0 and some same set of terminal payoffs at time H1, and you make different decisions. Maybe that doesn't sound so bad. Stuff's happened. Maybe you make different decisions. But remember, I said I'm going to exclude any non-zero payoffs at things which are inconsistent with H1. So in order for these bets to actually even be legal, I'm only offering you non-zero payoff at things that are extensions of H1. So it should seem strange that when non-zero payoffs are only offered on things that happen subsequent to history H1, it should seem strange that I would make different decisions at the start of time on that vector from at history H1. Okay? So making different decisions on those bets, I would say, is a form of inconsistency, dynamic inconsistency, meaning inconsistent across time. And it turns out the existence of such an inconsistency is equivalent to being non-Bayesian. Anyone non-Bayesian has such an inconsistency, and also equivalently, there will be a strong Dutch book against you. Yes.
When you say the decision maker makes different decisions, you mean accepts or does not accept the bet?
Yeah, accepts one, rejects the other. Yes.
But you're still talking about bets on the final state.
Yes.
So when you say they make different decisions, I mean, if I see
So it's like it's a
I mean,
bet.
you might channel like what if H1 makes you think the probabilities are different? I mean, the point is so on empty sets, you'll make bets on things which are not extensions of H1.
Right.
And after you see H1, you only
right,
make,
but because of the convention, this particular mathematical statement only applies to bets that are 0, because the same V in both places, and for this to be legal, V has to only offer non-zero things conditional on H1. So by convention, what I'm talking about is specifically that.
only is this one above. It's the only extensions of both H1.
Right, exactly. I'm only talking about things that are extensions of H1. So it's as if at time 0, I offered you a bet. That only ever does anything when we start with HTH, and then HTH happens, and now you want to change your mind. That's what that's saying.
The other thing that I don't understand is I mean, suppose everything was just IID, and you believed it was IID, and it really was IID.
Okay.
So it doesn't seem like there's any bets. What does that mean? I mean that.
So there would be bets that you'll regret, but you wouldn't be. So in other words, if I bet the first period is going to be H and then it's T, and
a weak Dutch book because everything is just completely uniform to you.
But you're not going to accept it. If everything's completely uniform, you're not going to accept a bet which is 0 some places and negative other places.
Oh, okay.
Right.
So, and just to clarify, so point 4, H1 and H2, one has to be a prefix of the other.
Yes, otherwise it's trivial.
Otherwise, it doesn't satisfy this.
Yeah, if one is not a prefix of the other, it's a vacuous
definition.
statement. Yeah, yeah, right, right. Yeah, and I'm not trying to hide that. That's it's just I find it easier to work with this convention and then explain what it means. Okay, so Colabet, okay, shift protected. Okay, so there'll be a couple of senses in which this decision maker might be approximately consistent. Okay, one sense is there's going to be a certain set of bets where he behaves as if Bayesian. Okay, so what do I mean by shift protected? I mean whenever this is a bet that you're being offered a history H. So suppose there are two terminal states that come after the same paradigm shift H prime, then the payoff at those is the same. So in other words, subsequent to H, this thing H prime might happen where I'm going to switch models, do something non-Bayesian. Okay, but all the states that come after that, I'm being offered the same payoff. So basically, by the time I've gotten to H prime, my payoff is already determined. Okay, V of omega 1 equals V of omega 2 for all states following H prime. So basically, the fact that I shifted paradigms at H prime won't matter. Okay, because so I changed my conditional belief across things subsequent to H prime, but if all those have the same payoff, that's not going to matter. Okay. So I'm going to let the set of such shift-protected bets, call it W sub H. That's a vector subspace because it's defined by a set of equality conditions that makes it a vector subspace. If something's not shift-protected, I'll call it shift exposed. Okay. Okay. So one proposition that's not that hard is that, so given anyone, okay, with any system of provisional beliefs, if I only look at his behavior on all shift-protected bets, then he makes the same decisions as a Bayesian decision maker with a different prior. Okay, so this PF, okay, the prior of this Bayesian decision maker will not be the same belief in this theorem as the belief held by decision maker F at period 0. But there will be such a Bayesian who makes identical decisions on all shift-protected bets. In particular, if you happen to only face shift-protected bets, then even though you're not Bayesian, okay, so Mr. F can change his beliefs all sorts of ways. But, whether he's aware of it or not, he's making the same decisions as this Bayesian with this prior on all these shift-protected bets. So if he only faces those, he'll satisfy all my consistency conditions because he's the same as some Bayesian. So he won't suffer from Dutch books or anything like that. Okay. So whether or not you only face shift-protected bets is something that depends on the context. But it's certainly possible. Like maybe for instance, if you only ever bet on the next flip, those are shift protected. Or if you only if you're somehow self-aware enough that you know when there's a possible paradigm shift coming 5 periods away, and you don't make bets that depend on flips more than 5 periods away, then those will all be shift-protected bets, and you'll be consistent on those bets, despite the fact you wouldn't be consistent on other bets. Okay, so that's one proposition. Okay, so I want to get to make sure I have time to explain the main proposition. Am I supposed to stop at 12:50? Is it?
You do it. I have a class at 1.
Okay. So
some of the students do.
Okay. So the specified time is 12:50, right? Okay. Good. So the all right. So WH is a vector subspace we can define, we can break things down into an orthogonal sum. Okay, so for any bet, I'm going to talk about the shift protected component, which comes from WH, and the shift exposed component, which comes from WH perpendicular. That's going to be with respect to a certain inner product. So I don't know. It's the inner product that's natural, conditional on being at period H and having beliefs f of H. Okay, it's basically your expected value of the product, conditional on that belief. So, okay, yeah, that's what I just say here. That's how that inner product is defined. So then I have, these shift protected bets, which hopefully I've given you some sense of what those are. The perpendicular space to that, well, once you think about it, I don't want to spend too long on this slide, but basically the perpendicular set winds up looking like the set of bets that have zero expectation at each paradigm shift. So in some sense, you should think of the shift protected component, that's the WH, as things that don't depend on what happens subsequent to any paradigm shift. And the orthogonal component would be essentially things that don't depend on what happens before, right? So from the point of view of time h, my average payoff conditional on reaching any shift would look like 0 in this orthogonal space. Okay, so there's things, basically WH, things that only depend on what happens before the shift, WH perp, the things that have 0 expectation conditional on reaching the shift and then only depend on what happens after. Okay, and that's just a decomposition of the vector space. Okay, so I told you something at the start of the talk that the paper was going to be about your degree of inconsistency. Okay, so since the way I'm measuring inconsistency is by the existence of Dutch books, it makes sense that I'm going to measure the magnitude of your inconsistency by the magnitude of the Dutch book. And how should I measure the magnitude of a Dutch book? Well, the reason that I'm upset about the Dutch book is because it's a certain loss. I mean, that's what makes it look really stupid. Okay, it's that, if you're this decision maker and you face someone who knows you well enough to offer the right bets and right times, you lose $10 no matter what happens. Okay, and I'd like to talk about the magnitude as being the amount of the certain loss. So I say, here, the smallest absolute loss you experience in any state. Okay. If someone is optimizing this, they can always make it so it's actually the loss in every state is equal. So you should think of it that way. Okay, you should think of the magnitude of the Dutch book as I'm losing X dollars for sure, the magnitude is X. Because really, if I had a Dutch book that made you lose $1 in this state and $100 in this state, I could always offer you a rebalancing bet that you would accept that would offer you, some kind of gain in this state and loss in this state to make them all equal. Okay, so that's always what happens at the optimum anyway. So the magnitude you should think of as the optimum for the person designing the Dutch book is to make you lose the same amount in every state. Okay.
I'm confused about one thing. Is it not true that you can just scale all bets?
Yes. So I'm going to have some condition that says something about the scale. It's going to depend on the scale as well as on the things I said before. Okay, so what I told you before is you're going to have to, the magnitude of the Dutch book is going to depend on your subjective probability of reaching a paradigm shift, okay? But also, it's going to have to depend something on magnitude, okay, because the decision maker I described to you, as Jason noticed, is totally insensitive to scale. I multiply all the bets by 1,000,000, he still accepts it. So if I'm going to talk about the magnitude of the Dutch book, I'm going to have to talk about the magnitude of something involving the bets. So it turns out all I need to look at is the magnitudes of the shift-sensitive components of the bets, and that should make sense given what I've been telling you, that for the shift-protected components of the bets, like in those dimensions of the vector space, you're actually a consistent person, you're just like a Bayesian. In the other parts, you're inconsistent, so what's going to be important is the magnitude of your bets when I project onto that component of the vector space. Okay, and so that's...
Can't you assume that the shift protected component is just 0?
I don't know. I mean, so...
Why would someone make a Dutch book with these things that don't make any money as an orthogonal component to it?
They wouldn't. I mean, so that's one thing that's going into the theorem. I mean, it's... I mean, that's why that part of the theorem is true. Because, yes, I mean, adding components in the part where you're consistent is not going to help the designer make the Dutch book any bigger. So that's why, you know, the theorem is true, which says you can ignore them. Okay. So, okay, so, you know, let D, which is some set of bets, be a Dutch book. I'm going to separate each vector that you're betting on into, you know, the projection onto these two vector subspaces, okay, which are orthogonal to each other. And I'm going to let epsilon be, so what does this say? This is the probability at time 0, okay, that with which I think I will reach a shift. Okay, so in other words, I have some belief at time 0 that might change in different ways in the future. This is the probability that I think at time 0 I will reach some funny state, something that makes me shift my beliefs in a non-Bayesian way. So something like the 100 alternating heads tails, okay, is going to do that. That was the example of that. Okay, so then the conclusion is that the magnitude of the Dutch book, in other words, the certain loss, is at most that probability times the, so that those double bars are the sup norm of that vector. So you sum up the shift-sensitive components of the bets, and you take the sup norm of that. So what is that quantity? That is, you know, across all states, what's the most that I would possibly, you know, between now and the end of time, what's the most that I would possibly stake on shift-sensitive bets? Okay. So in an earlier version of the theorem, I actually had the bars on the inside here, which is actually a much, it took me a bit to realize that that's a much weaker statement. You know, this is a much stronger statement, which also happens to be true, fortunately. With the bars on the inside, then this would say the sum across all bets that you make or might make in the entire, you know, 2 to the 100th tree, okay, which could be a very large number even if you never make very large bets. So fortunately, it's true with the bars on the outside, okay, which is a much more interesting statement. Okay. So that's the proposition. So I mean, at this point, I should stop if anyone, you know, could use some more information on what exactly the proposition is saying, or anything like that.
I'm still missing how you normalized.
So the thing that's normal, I'm multiplying by the magnitude of the sum of the bets. So if you scale them all up, this scales up. Right? I mean, you know, if you scale everything up, the projection scales up, that sup norm scales up. So that's, you know, obviously you need something like that for the theorem to be true. Is that okay? Okay, well, you can ask again at the end. So, okay. So, I mean, one thing that's nice about this result, so note that, you know, there being a Dutch book against you, being inconsistent in that way, is a very objective thing. It says, objectively, you're an inconsistent person. Your bets are such that I can design something where you always lose $10. But the input to the theorem is a subjective probability. Okay, it's according to you, what are the chances that you reach a funny history where you want to make a non-Bayesian paradigm shift? So, this takes a subjective quantity and returns in the conclusion an objective quantity. So it tells you if you're not likely to make one of these non-Bayesian shifts, according to you, then you're not very inconsistent. Okay, so as I stated in the open, the idea is that if your model is such that you're not likely to reject this model, so this is almost sounding like classic hypothesis testing, right? If conditional on your model being true, you only reject your model with probability 5%, something like that. I mean, that's just the level of a classic hypothesis test. Then you're not very inconsistent, and you shouldn't worry too much about the fact that you're non-Bayesian. Okay. So once again, kind of summing up the result in slightly different words, which might be what I just said. If your initial subjective probability of reaching a non-Bayesian shift is small, and if your dependence of your bets on post-shift events is bounded, okay, so I have to worry about the magnitude of my bets, but only about certain projections of my bets, the degree to which you're subject to an objective death book is small. Okay. And this is, the whole thing was motivated in large part by thinking that we have a lack of full introspection. Like, it's hard for me to know what I might believe at every moment in future time. I mean, I don't want to think about every possible pattern that could happen in the sequence that would make me want to say, oh, I think it's following this pattern and it's not independent. Okay? But I don't need full introspection to apply proposition 2. Okay, I would need something like full introspection to apply, to calculate the probability of events at time 0. I don't need it to apply proposition 2 because I only need to know that a certain chance of shifting. I don't need to know exactly what the states are where I'll shift or how I'll shift or anything like that. Okay. And this is meant to correspond to basic statistical practice and say that even if it's non-Bayesian, it's not non-Bayesian in a terrible way. Okay, so you have a model, you act as if it's correct, but then, if something happens that's in some unlikely set of states, we might reject the model. Okay, and this is there's a long-standing conflict between this process of reject model, try a new model, versus, just be Bayesian, state a prior, and stick with it. Okay. And this is saying, they're not so much in conflict. I mean, there are good reasons to be Bayesian. It keeps you consistent and avoids Dutch books. But if you do this, somewhat non-Bayesian process, there's some kind of continuity. Okay, you're not too inconsistent. Okay, and that's it.
Questions? So this f function is hard to compute somehow. Like, how do you know when to accept a bet? Or how do you represent f?
So I guess the kind of idea I have in mind is that f actually is computable, okay, in the sense that, given any history, I'm assuming the person has some way of knowing what decision they can make. I'm not exactly modeling that, but I would like that to be a function that can be computed in reasonable time. You see a sequence, you decide on your beliefs. I guess what's motivating the paper is, at least intuitively, it seems like even if that f is computable, so suppose, for instance, that instead of f, let's take a different function, like call it g, that tells you you've seen some sequence, what's the probability the next thing is h. Okay, and let's say you can compute that. But if it, and So, and let's then say, according to Kolmogorov extension, once I have this function g that always tells me what I think one period ahead, I actually imply a distribution on the whole state space. Okay. But calculating the probability of events according to that distribution may be very hard, right? Because I have to calculate that function g along, every path. Okay. So, yeah, I haven't said. I want to leave, I want to deliberately leaving it open exactly what kind of thing f is, but certainly my idea is that f is something that you know that you can compute, but in order to make decisions, you have to do things you can't necessarily compute.
But actually, so if the designer of the Dutch book is also computationally bounded, maybe he can't offer you
Right.
bets that you can't evaluate.
Right, and in fact, that's very close to a classic objection to, people who want to say, why do we care about Dutch books, say, oh, the person would have to look inside your head better than you do in order to offer this Dutch book, okay? So, despite that argument, I still think that knowing that there exist Dutch books against you might bother you. It might say, this procedure is improvable in some way, right? So as soon as I'm non-Bayesian, I know that there exist Dutch books, and at least that would bother me a little. Okay, so the purpose of this is to say, there's some very precise sense in which, you don't have to be bothered too much.